This video introduces the topic of finding real and complex zeros as well as graphing polynomials. The learning outcomes are to use definitions of zeros, turning points, and end behavior to describe polynomial graphs. To find all real and complex roots of a polynomial by using the conjugate zeros theorem, the fundamental theorem of algebra, and the intermediate theorem, as well as the previously covered theorems. And finally, to use this information to graph polynomials. First, let's take a look at a graph to visually see the definitions of zeros and turning points. Here we see a polynomial graph, and where the graph touches or passes through the x-axis are the zeros, since when we plug in these x values into our polynomial function, the y value is 0. So we can use the label of zeros and x-intercepts interchangeably. Remember, we can find these x-intercepts, or zeros, by setting the factors of the polynomial equal to 0. So for this graph, we can see that x plus 3, or x minus a negative 3, is a factor, and we see that there is another factor at x minus 4. Since we see that the graph curves through the x value of 4. In fact, we will discuss more about what is happening at x is equal to 4 of this graph later in this video. Turning points are points where the graph changes from increasing to decreasing or from decreasing to increasing intervals. We can see from the graph that the y values are decreasing as we move from left to right on the graph. So we have a decreasing interval from negative infinity to about negative 2.25. Remember that the interval negative infinity to negative 2.25 is describing the x values, while the word decreasing is describing the y values of the graph. Then, from negative 2.25 to about 0, we see that the y values are increasing. So we have found that there is a turning point at the x value of negative 2.25 and the y value of about a negative 1,000. Again, we see a change from increasing to decreasing at the x value of 0. So there is a turning point at x is equal to 0 and y is equal to a negative 100. There is another change from decreasing to increasing when x is about 1.5. So here is another turning point at 1.5 comma negative 200. Therefore, we can say that we will find at least one turning point between two consecutive zeros. In fact, for this graph, we found 3 turning points, and we will explain this phenomenon later in the video. One last thing I want to mention about this graph is the end behavior of this graph. To describe the end behavior, we first talk about the x values to see which end of the graph we want to describe. When we say, as x approaches negative infinity, this means we need to look at the far left of the graph and ask, what are the y values doing? Looking at the graph at the far left, we see that the y values on the graph are approaching positive infinity. So we write this as x approaches negative infinity, y approaches positive infinity. Now let's take a look on the right side of the graph as x approaches positive infinity, and we ask, what are the y values doing? From the graph, we see that as x approaches positive infinity, the y values are approaching positive infinity. To practice end behavior, let's return to our parent functions and the handout where we graphed the parent functions. You may want to pause this video here and try your hand at writing end behavior for each of the parent graphs before I continue to do the same here. So let's go over the end behaviors of our parent function. So notice, as we're looking over here towards negative infinity, we're going to see that our y value still continues to be at 3. So we're going to write that as x goes to negative infinity, our y value goes to 3. So it stays the same. We can do the same thing as x goes to positive infinity. That means we're looking over here at x is equal to positive infinity. We see that our y values are still staying at 3. When we go to linear, as I go over here towards negative infinity, we see that our y values will keep going downward. So we find that as x goes to negative infinity, our y value also goes to negative infinity. When we're looking over here at x is equal to a positive infinity, our y values are going upward. So we find that as x goes to positive infinity, our y values go to positive infinity. Going to absolute value, as x goes to negative infinity, we're going to see that our y values are getting bigger and bigger, and they will approach positive infinity. So for absolute value, as x goes to negative infinity, we found that our y values go to positive infinity. Likewise, when we go to the right, we're going to positive infinity for the x's, and my y values are constantly going upward. So as x goes to positive infinity, y is going to also positive infinity. If we take a look at quadratic, what we find is that as x goes to infinity, our y values are going upward to positive infinity. So we're going to write down that as x goes to infinity, our y value goes to positive infinity. And if we go to, sorry, that was negative. If we go to the right, where x is going to a positive infinity, we see our y value also going to a positive infinity. So I'm just going to write it over here. As x goes to positive infinity, our y value also goes to positive infinity. Over here for our square root, notice we cannot go to negative infinity. However, we can go towards 0. So we would say that as x goes towards 0, our y values are also going towards 0. So notice our y values were up here, and as we're getting closer, as x goes closer to 0, the y values are getting closer to 0. But we can say as x goes to infinity that our y value is also going to infinity, as we can see them going upward here. And last but not least, on this page, we see that as x goes to negative infinity, that our y values will be going to negative infinity as well. And as x goes to a positive infinity, we see that our y values are also going to a positive infinity. As x goes to a positive number, y values are also going to a positive number. Now, one thing I do want you to notice is that our end behaviors are dependent on our domain and range. So if we look at our domain, we see how it's going from negative infinity to positive infinity, and we see the same thing here. If we come down to our square root, notice that our domain here is from 0 to infinity, so our x's over here are also going from 0 to infinity. So our end behavior is also dependent on our domain. Let's continue. For cube root, we can see as x goes to negative infinity, our y values are going lower and lower and lower. Hard to tell in this graph, but what we find is that as x goes to negative infinity, our y values are also going to negative infinity. And if we go to the right, we can see that as x goes to positive infinity, our y values are also increasing. So as x goes to infinity, our y values go to infinity. For reciprocal, we see as x goes to infinity this way, negative infinity, our y values are getting closer and closer to 0. So we're going to find that x goes to negative infinity, our y values are getting closer to 0. In fact, we put a little 0 with a little negative sign to show you that they're coming from below the graph. If we go to the right side, as x goes to positive infinity, our y values are getting closer to 0 as well. We find our y values are getting closer to 0, but we would say a little plus sign because they're positive numbers. The little plus and minus stuff you don't really need to know, but you do need to know what happens in terms of our graphs and our end behaviors. So let's take a look at this one over here. We can see as x goes to negative infinity, our y value, I'm going to write it right here. As x goes to negative infinity, our y values are going to 0, and they're going from above. And as x goes to positive infinity, our y values are going to 0 also from above. So we can see that right here. Finally, we can go to these last few and we see that we can say that as x goes to 0, again, that remember our domain, we can see that our y values are going down, 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 so our y values are going to negative infinity. As we go to the right, as x goes to positive infinity, we can see our y values are going to go upward ever so slightly, but they will go to positive infinity. So again, remember our x's are dependent on our domain and our y values are dependent on our range. If we look at our exponential here, as x goes to negative infinity, we see that our y values are getting closer to 0, and again we can say from above. And as x goes to positive infinity, we see our y values increasing forever, so we see that going up that way. Now for the sine graph, which is this last one that we have right here, things are a little bit different, because what happens over here at negative infinity is that this graph keeps doing this, going up and down. So we really don't have end behaviors for sine graph or cosine graph. So same thing here, it'll go up and down, and so we will never have our end behavior like we did for the other ones. Before we begin graphing polynomial functions, let's take a look at some simple polynomial functions and check out their end behavior. In the My Notes for this assignment, we have the following graphs: linear, cubic, and to the fifth power. Notice that each of these parent functions has the domain from negative infinity to positive infinity, and their end behaviors are the same. As x approaches negative infinity, y approaches negative infinity. And as x approaches positive infinity, y approaches positive infinity. If there had been a negative leading coefficient, the end behaviors would change, as does the graph. So that as x approaches negative infinity, the y values will actually approach positive infinity. Another thing I want to mention about these odd functions is that there will be at least one 0 for these polynomials, since we see that on one end of the y values are negative and on the other end the y values are positive. So somewhere the y value was 0. So there has to be at least one 0 in any odd-powered polynomial. The next set of graphs are those of even powers: quadratic, to the fourth power, and to the sixth power. Notice that each of these parent functions have the same domain from negative infinity to positive infinity, and their end behaviors are the same. As x approaches negative infinity, y approaches positive infinity, and as x approaches positive infinity, y also approaches positive infinity. If there had been a negative leading coefficient, the end behaviors would have changed, as does the graph. So that as x approaches negative infinity, the y values would approach negative infinity, and as the x values approach positive infinity, the y values would approach negative infinity. Notice that there is no guarantee that there will be at least one 0, since the ends are not going in opposite directions. This is what the intermediate theorem says. That if a y value is positive and another y value is negative, then there has to be at least one 0 between the corresponding x values. This is not the case for these even powers. Let's take a look at more complicated odd-powered polynomials. There are no complicated linear functions, so let's move on to the cubic function. The simple version is x cubed, and we see that it has exactly one 0. And we see that the graph curves through the x-axis. This curve through the x-axis means that the polynomial has one factor that is raised to the third power. So for example, we can graph y is equal to the quantity of x minus 2 cubed by using our transformation knowledge. That means it's translated 2 units to the right. And note that x is equal to 2 is the only 0 for this graph. A more complicated cubic function would have an x squared term as well as an x term, and maybe even a constant. And the number of zeros can change from only 1 0 to 2 zeros, or even up to 3 zeros, as shown by these graphs. Similarly, we can do the same for x to the fifth function and see that we can have 1, 2, 3, 4, or 5 zeros. These places where the graph is tangent or just touching the x-axis are caused by an even multiplicity of zeros or roots. This means that the polynomial has a factor that is squared or to the fourth power. Our conclusion is that odd power polynomials with power of n can have 1, 2, 3, all the way up to n zeros. And this is backed by the fundamental theorem of algebra that states that a polynomial function will have at most n number of distinct zeros, if n is its highest power. Now let's look at more complicated even polynomials. For the quadratic function, we see that it can never touch the x-axis, or maybe just touch the x-axis, or it may have two x-intercepts. So we see that even functions can have 0, such as x squared plus 4, or 1 0, such as the quantity of x minus 4 squared, or 2 zeros, as in x squared minus 4. We can do the same for x to the fourth function and find 0, 1, 2, 3, or 4 zeros. Our conclusion is that even-powered polynomials with the power of n can have 0, 1, 2, 3, all the way up to n number of zeros. And this again is backed by the fundamental theorem of algebra. Again, I want to remind you what happens graphically when we see factors raised to exponents. So for example, if we have p to the x is equal to negative parentheses x minus 2 times parentheses of x minus 3 squared times x minus 4 cubed, we should see that this is a polynomial of degree or highest exponent of 6. If we were to multiply this out, we would have x from the first factor, x squared from the second parentheses, and x cubed from the last parentheses. And when we multiply x times x squared times x to the third, we get x to the sixth. From the exponents on the parentheses, we know that the graph will go through the x-axis at x is equal to. The graph will only touch the x-axis at x is equal to 3. We see this from the square power on the x minus 3 factor. And finally, the graph will curve through the x-axis at x is equal to 4. Because this is an even-powered polynomial and the leading coefficient is negative, we know that the end behaviors will both be going down. So far, we have only dealt with real zeros, but when we are solving quadratic equations in the last unit, we found that some zeros, that means the x values can be plugged into the polynomial and the y value would be 0, can be complex or non-real. The conjugate zero theorem states that if there is a complex zero in the form of a plus bi, then you also have a complex zero in the form of a minus bi. Even though we find complex zeros of polynomial functions, we cannot graph them on our xy plane, but we do see them and the turning points between the real zeros. Let's take a look back at our first graph and see if we can apply what we have discussed. From the end behaviors, since both ends are going up, we know that the graph is an even-powered function, and the leading coefficient is positive. At x is equal to -3, the graph goes through the x-axis, so x plus 3 is a factor and the parentheses has an exponent of 1. At x is equal to 4, we see that the graph curves through the x-axis, so we know that the factor of x minus 4 has a power of 3, or 5, or 7. But since we will be looking for the least power polynomial, we would use the power of 3. So we can write that our polynomial can be p of x is equal to some coefficient number, positive, times x plus 3 times x minus 4 cubed. And this will be an intercept form since we are creating p of x using our x-intercepts, or the zeros. We also need to make sure that the graph goes through the y-intercept of 0, negative 100, as shown in the graph. So let's plug in our point x is equal to 0 and p of 0 is equal to negative 100 into our factored form. We will get negative 100 is equal to a times 3, because 0 plus 3 is 3, and then parentheses negative 4, because 0 minus 4 is negative 4, and then we're going to cube that. And we solve for a, and we will find in this case that a is equal to a negative 100 divided by 192. This is assuming that all the zeros are real. If there were complex zeros, we can have our p of x to be a times x plus 3 times x minus 4 cubed, and then let's say x squared plus 1. Since we know that if we solve x squared plus 1 is equal to 0, we would see that x is equal to plus or minus I. Notice that we get our complex conjugate zeros of positive I and negative I. Now our polynomial has a degree or highest power of 6. X from the first parentheses, x cubed from the second parentheses, and x squared from the last parentheses. We would still plug in our point, the y-intercept, to determine the value of a. Finally, you will be asked to graph polynomials. The first step is to find all zeros, real as well as complex zeros. This is when you will use the rational root theorem to find possible zeros to guess. You use synthetic division and your guesses and see if you find a remainder. If you do have a remainder, you have found a point on your graph, where the x value is your number in the small box for the synthetic division, and y is the value of the remainder. If the remainder is 0, you have found a 0, which means you have found the factor of x minus a. Remember, a is the guess that was in the small box of the synthetic division. Once you have found a 0, you can continue finding zeros of the quotient to find the remaining zeros of the original polynomial. So if you started with an x cubed polynomial and you found a 0, the quotient will have an x squared polynomial that you can use by solving quadratic equation skills from the last unit, so that you can solve for the remaining zeros. Once you've found all the zeros and their multiplicity, that's the exponents for the factors, graph each of the points on the x-axis. The second step would be to find the y-intercept of your polynomial p of x by plugging in x is equal to 0 and finding the y value. And finally, use your knowledge of even and odd powered functions, and in particular their end behaviors, to complete the graph. There are a couple of video examples that you may want to watch to get the hang of graphing polynomials. And this concludes this video.